All right, let's talk about Resonant Frequency Lab. Resonant Frequency Lab has two parts. Let's start with part one. Part one, our goal is to find spring constant K. So in order to do that, our setup looks like something similar to what you see here on the screen. Okay, so what I have a box or a glider in this case with mass M here. It is connected to a spring system here. The spring system is fixed at one end and connected to the box on the other end. Okay, so the goal for part one is to find spring constant K. In order to do that, the first thing we need to do is to mark where the relaxed position of the spring system is. So let's say that we can measure the relaxed position of the spring to be somewhere here. Okay, I mark this as the relaxed position. I call it X1. Okay, so the relaxed position is X1. Okay, so I'm measuring the distance from this point, all right, and the relaxed position that the spring system is not stretched or compressed, I call it X1. All right, now let's say that I connect this system of a spring and mass to a pulley with a string, and on the other end of the pulley I have a mass holder. Okay, I have a mass holder. I can add masses as I want. So let's say that the mass of a mass holder is M1 in this case. Okay, mass of the spring, mass of the glider or the box attached to the spring is M, and mass that's hanging here is M1. All right, this M1 is a mass of a mass holder connected to the string. String is connected to the box. So let's see how many forces we have. So starting from here, we have normal force upward. We have gravitational force, mg, okay, and we have tension from the string, T. On this side, we do have force of spring, F of S. In this case, it's not friction, static friction or anything. I'm just using it F sub S just to indicate that it's from the spring, okay? On the other side, when we have a hanging mass, we have force of gravity, M1G, and we have tension upward, okay? When the equilibrium happens, meaning that the system is not moving, it's done stretching and things like that. When the equilibrium happen for the hanging mass, I have T, which is the tension in the string, equals to force of gravity and 1G. Okay, I'm talking about these two. And for the box attached to the spring, I have N equals mg, and I also have T equals force of a spring. I'm going to highlight the two forces that I'm going to use. This force, or this formula, from the hanging mass, and this one. Looks like tension is equal to M1G for the hanging mass. It's also equals to force of a spring. Okay, so in other words, from these two, I can conclude that force of a spring is m1g. I'm going to put this in a box because I'm going to use it. So this is important. And we do remember from spring force that the absolute value for spring force, or force of a spring, is negative kx. K is a spring constant. It's a constant number. That's what we're looking for in part 1. And x is the amount of displacement from the relaxed position. So when I'm hanging some mass here, it caused this box to be stretched a little bit from this x1, which is here, to some other x, being stretched along the x direction. So after the hanging mass is attached to the string, then we'll have x2. It's not x1 anymore because that hanging mass is causing the system to stretch a little bit to the right. Okay? And here, this x is simply the difference, okay? This one is the displacement, so this x is simply x2 minus x1. This is the amount of a stretch or compression on the spring. Okay, so again, just to review, I have a hanging mass with force m1g. This m1g causes the box or the glider connected to the spring to be stretched slightly, going from relaxed position x1 to stretch position x2. Okay, the difference between these two numbers is the amount of a stretch from x1 to x2. So this x is the difference between the two positions, or in other words, the amount that the spring is being stretched. This k is the spring constant. All right, so what I do have, using that equation in the box and using this, what I have in the left-hand side, I can write that f of s, which is equal to mg, I can rewrite this and write it as kx equals m1g. All right, so what I have is hanging mass, which I can measure, gravitational constant g, k is the spring constant, and x is the amount of stretch. If I solve this equation for k, this is exactly what I'm looking for. I'm looking for k, or a spring constant, in part 1 of the experiment. K is m1g divided by x. So gravitational force on a hanging mass divided by amount of stretch will give you spring constant. So the first part of the experiment, you are going to have a table. I recommend to have a table for part 1. So let's say we actually only might need only 2 columns and multiple rows. So hanging mass, all right, and we can call this one displacement. Okay, displacement is simply just x final minus x relax, or in what I showed, x2 minus x1. Final position minus the relaxed position. So if we add m1, we had x2 minus x1. If we have m2, we would have another x, x3 minus x relax. If we have m3, we would have another position. I don't know, we can call it x4 minus x1. The idea is this. If I keep adding masses, let's say mass number 4, I would have x5 minus x1. If I change this hanging mass, so let's say that 50 grams, and then I go to 100 grams, and then I go to 150, then 200, 250, and so on and so forth, the amount of a stretch I see from the relaxed position would be different. So for 50 grams, this much of a stretch I would see. For 200 grams, I'll see more stretch. Okay? The idea is this: hanging mass times gravitational constant divided by the amount of a stretch. This is final minus initial, okay? Which is final minus initial, final minus initial, final minus initial, final minus initial. Pay attention to that. All of these initials are the same. They start from all of them are relaxed position. For M1, the final position is that. For M2, the final position is X3. For M3, the final position is different. And the amount of a stretch or displacement would be different. Okay? The idea is that you would have a K number here. All right, so that would be M1G divided by the amount of a stretch, X2 minus X1. You would have a different K value here, M2G divided by X3 minus X1. K would be different for this child, would be M3G divided by X4 minus X1, and so on and so forth. So you have multiple calculations for K, which is the spring constant, and then you can make an average. All right, so what you're going to use is the K average, whatever it is. Okay, so that's part one. The goal for part one was to find spring constant, and we reached that goal basically. On part two, we're going to use that K, okay, to find the resonant frequency. The resonant frequency is a very interesting topic. So you'll see later throughout this video what the resonant frequency is and what it looks like. But the resonant frequency for the spring that we use theoretically should be 1 over 2 pi square root of K divided by M. This M is mass of the cart. Okay? Mass of the cart or mass of the box, mass of this object right here. Okay? K is that same K that you found here. This is the same K that we have here. All right? And 1 over 2 pi, pi is 3.14. So in other words, we can find what the resonant frequency for this particular spring is based on the K value that we found in part 1. All right? Again, this F is the resonant frequency. It's 1 over 2 pi square root of K, which we found in part 1, divided by M, mass of the cart. So this is the theoretical value. This is what you expect, the expected value. All right? However, the actual value will come from the lab. The idea is this: we would have a frequency generator. It looks like a little box. You will see it in the video later on. And it has a knob. You can change the frequency. This will go to a coil, all right? A coil. And then we'll attach the coil to that same box with mass M. We'll bring it actually very close. Same setup, spring with constant K. And one side is attached to the wall or something, and the other side is connected to that cart. And we'll have a magnet. So this is a magnet here. And what's going to happen is this. This frequency generator is generating a frequency in this coil, all right? And this coil would be interacting with this magnet. This magnet cause the system, the box, or the card connected to spring to vibrate, to go back and forth. Maximum amount of vibration would happen at a particular frequency, which we call the resonant frequency. Okay, so let's say the resonant frequency for a particular mass spring system would be at frequency, I don't know, 4.75 hertz. All right, hertz is 1/2. Let's say that's the case. That would be the experimental value, and then you want to compare it to expected value that you have here. So again, frequency generator connected to a coil. Coil is interacting with a magnet. Magnet caused this system to go back and forth because it's attached to a spring. All right, and whatever frequency that you see on the screen would be the frequency that's being put out to this coil. Maximum amount of vibration would happen at a particular frequency. That particular frequency is called resonant frequency. That is your experimental value, and then you want to compare it to theoretical value. In the next few minutes, we'll show you the setup and we'll provide you with the data. First part of the experiment, we're going to measure the mass of the glider using a 3-beam balance or any other way. In this case, I'm reading 179.7 or simply 180 grams. Next, I will attach the spring to the glider and simply measure the relaxed position of the glider and the spring system. We are going to connect the spring glider system to a hanging mass. We're going to use a string and a pulley, which is considered to be frictionless, and the gravitational force on the hanging mass will stretch the spring system to a final position different from the relaxed position. The mass of a mass holder is about 50 grams. We'll add 100 grams mass, so the total is 150 grams, and we'll measure the amount of stretched from the relaxed position. We'll keep adding masses, in this case another 200 grams, and again measure the amount of stretched from the relaxed position. We're going to remove the string and add a magnet for the next part of the experiment. We're adding the coil, which is connected to our frequency generator, and a frequency generator can generate frequency with different frequencies being generated throughout that coil. That coil will in turn be interacting with the magnet. So right now we're connecting it to the frequency generator that can generate frequencies with different amounts. We're going to use the air blower to reduce the amount of friction, and as you can see, the glider starts to oscillate back and forth at a particular frequency, which is not known or not determined yet. We'll have the maximum amount of oscillations. So we have to change the frequency in our frequency generator until we see the maximum amount of oscillations, as you can see here on the screen, being generated. And we have to actually measure the amount of displacement using a little cardboard or any other way that you can measure. We can measure the maximum amount of displacement. That frequency that we see the maximum displacement in the card and magnet system is considered to be the resonant frequency, and then we have to compare it with the expected value that we get from the equation.